Okay, we're now going to move on to the concept of humoral immunity. So, humoral immunity is indirect. Cellular immunity was a direct lethal hit. This is going to be indirect. You're going to have your plasma cells, the effector cells, that are going to secrete antibodies, and antibodies are going to come tag bacteria and things like that for destruction by the phagocytes. So this is a little bit different than what we saw before. All right, so the B cells are the players here, again, developed in the bone marrow. These guys are homeschooled. They don't get to go away to University of the Thymus. They are going to go through a very similar process as your T cells, but they're going to do it in the bone marrow. Anything that reacts to a self-antigen is going to die, and it's going to leave you with what are called self-tolerant B cells. And they're going to make a bunch of clones once we have determined that they have a good antigen receptor and don't react to self. From there, they're going to head out and deploy out to the same workstations as we would see the T cells do. Okay, let's talk about B cell activation. We didn't go too far into this with T cells, but we're going to look at it a little bit more closely with the B cell lines. Okay, we're in a lymph node somewhere, all right? And we've got 3 different types of B cells. Their surface antigen receptors are different. This one could bind to triangle, this one can bind to circle, and this one could bind to square. Okay, so this is that concept of the lock and key that we're talking about. So let's say that they've been sitting out there, and it's been, you're 20 years old. So this guy right here has never seen its antigen before. And suddenly, here it comes. You have finally been infected with Circle. This guy is going to get super excited. It's going to bind to its antigen that it fits with. It's going to process it. So remember we talked about antigen processing. And it's going to take that antigen and pop it out on its MHC2 hot dog bun. Now we know that MHC2 targets the helper T cells. So the helper T is going to come in. It's going to take a look at the antigen and say, all right, let's see. Is this something good? Should we be forming immunity against this? Let me look at it. If it determines that Circle antigen is an okay thing to form immunity against, then it's going to, via these cytokines, which are generally interleukins, it's going to tell the B cell, go ahead. Okay, so this process right here was when the B cell is running up to the T cell going, T cell, T cell, T cell, I finally found my antigen. I have been waiting to see Circle my whole life, and I have finally found it. Can I make my antibodies? And helper T is going to look at it, make sure Circle's okay, give it the go-ahead. Now we go through clonal selection. This B cell is going to make clones of itself. Now remember that this is only one of these 3, and it's the one that had a receptor that could bind to Circle. So that's what we're making clones of. This is the one that got the okay from the helper T. So this is the only one that can do this. And it's going to trigger a whole bunch of mitosis. And during this time out in the lymph node, your lymph node is swelling up because there's so much mitosis going on in there that it's actually getting bigger. And that's what happens when your lymph nodes swell, is it's actually an indication that your immune system is working. Through the mitosis, we're going to differentiate into 2 populations, the plasma cells and a memory cell. Okay, so 2 different versions of this. Let's talk about the plasma cells first. They are going to secrete the antibodies. And look at what an antibody looks like. So let's look at this and come up here and look at what that surface receptor looked like. The surface receptor is an exact replica of the antibody that this cell is capable of producing and secreting. So we know what the antibody is going to look like. It's going to be able to bind with circle. They are now going to be released, and they're going to go tag everything that has that circle antigen on it for destruction. So if we compare a plasma cell to a regular B cell, first of all, they are bigger. So it's a plasma cell versus a B cell. They have far more endoplasmic reticulum, the rough ER in here, because that's where we make these antibodies. They don't live very long. They only have a lifespan of about 4 to 5 days, but while they're alive, they secrete about 2,000 antibodies a second. So that is a huge influx of these antibodies into your blood or your tissue fluid, which is going to absolutely flood your body with something that can now deal with this extracellular pathogen. So that's what's going on with the plasma cells. Now the question is, what are we going to do with this guy? What's going on with the memory cell? The memory cell you can think of as pre-authorized. This whole process here takes a minute. The B cell's got to go find a T cell. It's got to tell the T cell what it wants to do. The T cell's got to look at the antigen. It's got to secrete the right molecules to tell the B cell it's okay. It's going to take a little bit. Memory cells, because they are an exact clone of this cell, which got the okay from the helper T, they are pre-authorized. The next time you see circle, you're going to respond much faster because you don't have to do this. You already got the helper T's okay. So let's look at this concept of memory. So during a primary immune response, it's going to take a few days from the point that you're exposed, and you're going to get a little bit of antibody. Not too much, though. The second time you see this, so during this period right here, that's when all of the, checking with the helper T cell and things like that is going on. So you've got this lag before you even get antibodies, and then you don't get that many. I mean, enough that you don't die or anything, but, it's not all that impressive. Look what happens when you get a secondary response. From the exact minute that you are exposed, you get a massive amount of antibody. So not only is your secondary response faster, it's stronger. This is what we mean by adaptive. When we say that it gets better at its job over time. So the more times you see an antigen, the stronger your immune system becomes against it. So that's the concept of memory. That's what that pre-authorizing is for. It's so that when you see it the next time, you get an immediate, very strong response. This is also a good time to talk about that artificial active immunity that comes from vaccines. What a vaccine does is it gives you a primary response and gets you memory. So the primary response is not that great. So we inject you with a non-pathogenic or a non-virulent version of the antigen so that we can stimulate your immune system to go through that primary response and get memory. That way, when you come across the virus or bacteria in its true virulent stage, you're going to get this response. You're going to get the immediate, strong response that occurs when you already have memory. That's why vaccines work. That's why they are important. So they are giving you a controlled primary response. And no, you cannot get whatever it is from the vaccine. The virulence factors have been removed. You don't get the flu from the flu vaccine. But when you run into the flu after having the vaccine, you get this response instead of that one. Okay. Now let's talk about the antibodies. So these are what are called your immunoglobulins. They are your gamma globulins, which you should remember were part of your plasma proteins. These are the only ones that were not made in the liver because they are going to be made by your plasma cells, your B cells. So we find these pretty much in fluids. So we've got our plasma and tissue fluid, secretions like tears, breast milk, and then we also find them embedded in membranes. They are a Y-shaped molecule that have variable and constant regions. I like to think of them as lobsters. So everybody picture a lobster. It's got its body, and then it has two pinchers, okay? The variable region would be the lobster's pinchers. It's very specific to the shape of the pincher and what it could grab a hold of. The constant region is the same within each of the 5 classes and would be the body of the lobster. So picture that you have 5 different lobster bodies and an infinite number of claws that could go on them. The body determines the action. So the constant region determines what the antibody will do and how it will function. So the 5 classes are IgA, IgD, IgE, IgM, and IgG. How do we get an infinite number of claws? 2 ways. First of all, we've got the endless combination of the genes that I was talking about before with T cells. This is called somatic recombination. This is like taking the 26 letters of our alphabet and making an infinite number of words out of them. We just keep rearranging the genes and we get a brand new version, a brand new word, if you will. But then also the B cells undergo hypermutation out in the lymph nodes and things like that come up with completely novel versions of this. Now, can this be a problem with autoimmunity? Sure. We'll talk about that later. But it is a source of variation for us and how we get this. There's estimates that, like we have the ability to make over 1 trillion different variable regions or the pinchers on the claws. So now let's talk about these classes. I'm going to go through characteristics of each of these classes that you should be familiar with. So we're going to start with IgA. First of all, it is generally formed a dimer. Okay, we usually find it in a dimer formation. This is known as your secretory antibody. So it's going to be in fluids that are secreted. So it's in plasma, but it's also going to be in mucus, tears, breast milk, saliva, intestinal secretions, vaginal secretions. And so it's secretory. And then oftentimes it's just called secretory IgA. In terms of a kind of relating this back, when we talked about natural passive immunity coming from the mother, IgA is responsible for natural passive immunity to the newborn via breast milk. Okay, so once the infant has been born, IgA is responsible for natural passive immunity. IgD, we don't know that much about, other than it is a receptor on B cells and likely is going to function in their activation. That's as far as we have determined what's going on with them. IgE is going to be a receptor in basophils and mast cells. So these are going to be responsible for what are called type 1 hypersensitivities. So we're going to get into disorders in a bit. And type 1 hypersensitivities are IgE mediated. So when we talk about anaphylactic reactions, we're talking about IgE. IgG is your primary, so the most abundant antibody that you have, it is also very, very small. Um, it is secondary. So when you have a primary immune response that we just talked about, IgM is the first one that you're going to form. Then you transition to IgG. So all of your long-term immunity is in the form of IgG. Because it is so very small, IgG crosses the placenta. Therefore, IgG is responsible for natural passive immunity to the fetus. So while you're still in utero, it's IgG that is conferring immunity. But because it crosses the placenta, IgG is responsible for incompatibilities within the Rh blood system between mother and fetus. So IgG is responsible for hemolytic disease of the newborn. IgM is generally found as a pentamer. So you've got 5 of your lobsters hanging out together. Their tails are all facing in. Obviously, it is the largest of the antibodies. It is going to be the antibody that is made first. So it is your primary immune response antibody. IgM is responsible for transfusion reactions within the ABO blood group. So IgG is responsible for reactions within Rh. ABO is going to be related to IgM. So you can see that sort of each one of these is going to have its own kind of thing going on with it, whether it's first, it's second, it's long-term, it's secretory, deals with very specific cells like a B cell or a basophil or a mast cell. All of them are playing their own role. Now, what do? Handful of things. First of all, when an antigen and an antibody bind, you're going to get a complex. Okay. So, first thing that an antibody could do would be an inactivation of some sort. So let's say it's a toxin. We could neutralize it by simply surrounding it with antibodies. Agglutination. This is what happens when you're dealing with a cell-bound antigen. And so this is an ABO reaction where the IgM actually binds to multiple cells and clumps or agglutinates them. If you have a soluble antigen, precipitation is very similar, except you're not dealing with the cell because now you're just dealing with the antigen here. Now, all of these are going to stimulate phagocytosis. So, this is what's going to have to happen. Remember that opsonization is going to function here, and antibodies are part of that bacon and cheese we talked about. So when we cover this with antibodies, or stick these cells together with antibodies, or precipitate these antigens out via antibodies, it's going to draw in the macrophages to eat whatever this is. Another thing we could do is fix complement. So whenever there's an antibody present, it's going to help complement work better. And we know what complement does. We know that complement helps out inflammation, helps out phagocytosis via opsonization, and also, due to the membrane attack complexes, leads to the lysis of the cell. So there are a handful of things that antibodies can do, but usually we're going back to our kind of second lines of defense in what's really going to occur here in terms of how to get rid of whatever we are bound to. All right, so humoral immunity, we got our receptor that fits. We go find a helper T cell. We're very excited. Helper T cell says okay. So we're going to differentiate into plasma cells and memory cells. Plasma cells start spitting out a whole bunch of antibodies. They tag your bacteria. Here comes your macrophage. It's going to come in and it's going to go, oh my gosh, there's antibodies everywhere. I got to eat this thing. It's going to eat it. And then you also have a memory cell that's like, hey, I remember you, and is able to respond very, very quickly.